So, no review of biochemistry would be complete without spending some time talking about water. Water is a really interesting molecule. It's inorganic. We tend to think of the chemistry of living things be about molecules that contain carbon, so organic molecules, but water is actually an inorganic molecule. And what water is it's a solvent. So basically, many of the chemical reactions that occur in living systems happen in water. So water is actually there. Sometimes it's participating as an intermediate. Sometimes the other molecules are just dissolved in it. A water molecule is really unique. So a water molecule has an oxygen and two hydrogens. If you remember from taking your chemistry class, oxygen is electronegative. That means it really likes electrons. It tends to hold them really tightly to it. Hydrogen, on the other hand, is simply a proton and an electron. It's just those two particles. And because it only has one electron, oxygen tends to hold those electrons. It tends to pull hydrogen's electrons really close to it. And that results in a charge differential. So you have sort of a negative charge on one end of the molecule and a positive charge on the other end. It's not a full negative and a full positive charge. We call it a delta minus and a delta plus. So they're partial positive and negative charges. And this allows water to do something really unique. So because of the partial positive charge on hydrogen and the partial negative charge on oxygen, water molecules are attracted to each other. And so you have the oxygen of one water molecule attracted to the hydrogens of other water molecules. And even though this bond isn't as strong as a covalent bond or an ionic bond, it's still a strong enough bond to have a special name. It's called a hydrogen bond. Hydrogen bonds are, in liquid water, they're constantly being formed and breaking and formed and breaking, but they're enough to cause these molecules to be very sticky. So water molecules tend to stick to each other a little bit like Velcro, and it's because of this property of hydrogen bonding. Here's another picture of hydrogen bonding. This shows 5 water molecules, and you can see that there's a partial positive charge on the hydrogen, and it's always facing the partial negative charge on the oxygen. So here we see it here. You can see the hydrogens are always oriented towards the oxygens for all of these water molecules. Now think about a little bit of vegetable oil that maybe you've spilled on a countertop. That oil is going to spread and form a really thin film. And it does this because oil molecules, the interactions between those molecules are non-polar interactions, and we call them van der Waals forces. And even though they exist, they're weak. And so there isn't a strong attraction between those molecules. They're going to spread out, and they're not going to stick to each other particularly well. Water, on the other hand, water molecules are very attracted to each other. So if you spill a drop of water on a countertop, it's going to form a bead. And that's because the water molecules are actually holding, the hydrogen bonding is holding the water molecules together and resulting in this sort of formation of surface tension that you're probably familiar with on the surface. Hydrogen bonding also gives water some other characteristics. So it takes a lot of energy because of the hydrogen bonds. It takes a lot of energy to actually cause water molecules to separate from each other. And when we go from a liquid to a gas, it's a phase change, right? But it takes way more energy to cause water to go from a liquid to a gas than has a molecule with a similar molecular weight like methane. So for example, methane and water have almost the same molecular weight. You would expect, all other things being equal, that if methane was a gas at room temperature, water would be a gas at room temperature. But in fact, they're not at all that way. Methane is a gas and water is a liquid. And that's directly to do with the fact that these water molecules really want to stick to each other, and therefore it takes a lot more energy, a lot more heat to cause them to form a gas. And so water doesn't become a gas until 100 degrees Celsius. So this characteristic is called the specific heat capacity in chemistry. And this actually is really important to life on Earth because it means that water molecules in the oceans, which cover a tremendous portion of our planet, the oceans themselves can absorb a tremendous amount of heat, and they can release a tremendous amount of heat to keep the planet's overall temperature fairly stable. So the water on our planet acts as a big temperature buffer. Other planets have very extreme temperatures. They're incredibly cold at night and incredibly hot during the day. They go through these, several hundred degrees of temperature change in a single day, not necessarily 24 hours on another planet, but in a single day on that planet. And yet on Earth, our temperatures stay, we think it gets cold and warm, but really compared to other planets, it's just nothing. We have a very temperate planet. Some of that is the atmosphere. A lot of it has to do with the amount of water that's on the Earth and the fact that water has this specific heat capacity and keeps our planet comfortable and very temperate. The temperature is very stable. Life likes consistency. So it's a lot easier for living things to survive and evolve and where the environment is more stable. Water is so important that when you hear scientists talking about life on other planets, they almost always ask, the first question they ask, we discovered a new planet, the first question they ask is, did they find water on that planet? And then they look at other features of the planet to see whether or not it might be conducive to life. But water, at least the way we understand life, water is a requirement. And that doesn't mean we won't find life out in the universe at some point that looks completely different and doesn't rely on water, but the way we understand it, water is certainly necessary. Let's go back a slide there. So I mentioned phase changes a little bit ago, and another really interesting property of water is the fact that ice floats. Generally, as things get colder, molecules or a solution of molecules would get denser. So for example, you would expect with warm water that there's more energy, the molecules are vibrating more, they're going to be a little further apart in warm water. And then when you get to cold water, you can see that there's less kinetic energy in those molecules and they're a little bit closer together. So when you have warm water and cold water, you tend to see the warm water on top. But this would argue that there should be ice at the very bottom of the water, and that's actually not what happens. When water organizes and changes phase from a liquid to a solid and forms crystals, the crystal pattern actually forces the water molecules to be further apart. And interestingly, this feature is what you see if you pour, ice, if you pour water into a cup of ice, the ice will float. And this is what you see in the oceans as well. You see if in places where the water is cold enough to be frozen, you have a layer of ice on the top, but underneath the ice is all these living things that have not been frozen. And this turns out to be really important for life on Earth as well. We talked about this idea that maybe life evolved in hydrothermal vents under the ocean. There's a lot of really important life that occurs. And if water froze from the bottom up, that may have prevented the evolution of life as we know, or many of the ecosystems that exist on Earth. So this idea that ice floats is also another feature of water that makes it conducive to life. All right, I said on the first slide that water is a solvent. So what do we mean by solvent? This is a sodium chloride crystal. So if you put a little salt on your French fries, this is what you're adding to your fries. So this is sodium chloride. These are the sodium atoms, they have a positive charge. These are the chloride ions, they have a negative charge. And so they form this beautiful little crystal, and you can see, like any electrostatic attraction, you have the negative charges always aligned to face the positive charges. So every chloride ion is surrounded by sodium ions, and every sodium ion is surrounded by chloride ions. If you take a crystal of sodium chloride and you put it in water, you can shake it and make it dissolve quickly, but if you do nothing, it will still dissolve. So what's happening? Well, remember that we said that water is polar, right? It has negative charges and positive charges. Well, it turns out that a sodium atom can be surrounded by water molecules with the oxygen facing the positive charge. So this is called a shell of hydration. And you can see what happens is, and it does this spontaneously, the water molecules will surround the sodium atoms, and then they'll also surround the chloride. And you can see here, now we have the positive hydrogens, the delta plus on the hydrogens surrounding the chloride. And so water is actually able to, gone back to my slide, water is actually able to form these shells of hydration around ions and pull them into solution. And so very quickly, water will take this, and all of these sodium and chloride ions will be dissolved in the water. So again, water is a solvent because these ions are dissolved in the water. And it's not just sodium chloride that's dissolved in water. Many things dissolve in in water. So this is actually hydrochloric acid here, and this is sodium hydroxide, and here's sodium chloride. But it's not just these molecules. It's many proteins, it's carbohydrates, things like glucose are soluble in water. So there are many molecules in biology that are soluble in water, and the chemical reactions that are happening in your body, in your cells at all the time are, your cell is basically a bag of water with many, many things dissolved in it. All right, so this is just a cute cartoon. This is Beatrice, the biologist, and here we have a sodium ion and a chloride ion, and they're bonded together in an ionic bond. And sodium says, I just love hanging out with you, chloride. And chloride says, hee hee, sodium. And sodium says, oh no, is that water? And chloride says, what, where? And then, they get these shells of hydration, right? The water molecules, and you see how they're oriented properly. The negatively charged oxygen is surrounding the positively charged sodium, and the positively charged hydrogens here are surrounding the negatively charged chloride. And sodium says, I'll never forget you. So this is a cute little cartoon, but it's illustrating these shells of hydration and the process of how water acts as a solvent. Okay, so that's it for water, and next we're going to be talking about organic molecules.